PhD IIT Madras
आईटी खड़गपुर से, हाँ, वो बहुत लंबा है। कुछ जब बात नहीं आप बोलो कि he is doing mathematics science
सब ठीक है। एक्चुअली आपका कंडेंस मैटर में है ना,
एटॉमिक फिजिक्स।
एटॉमिक फिजिक्स थ्योरी।
समझे मैं इतना बोलने की जरूरत नहीं है।
Okay, I'll just give one more minute. हाँ, गोपाल आप बैठ जाइए। अभी एक्सपेरिमेंट जरूरत नहीं। Okay, while people are coming in, let me start. So let me welcome one and all for this edition of the Wednesday Colloquium, and we are glad that an institute nearby, it's 1 hour away, 1.5 hours away, depending on the traffic. We could pull our speaker today, Professor Gopal Dixit, who does a lot of very exciting work on attosecond science, does computationally model things, and tries to understand how electrons behave after being excited with pulses, or at a very fast time scale, can you image electron motion and things like that, associated areas of science. Gopal, of course, we'll talk about that, but before he goes into his colloquium, just wanted to tell Gopal that this is the oldest event in the institute. This was started by our founding director, Professor Homi Bhabha, and it brings in people from different disciplines together. So thank you for coming by, stopping by, and giving us a broad overview of your activities. Gopal actually did his bachelor's and master's from Allahabad University in physics. And then he joined IIT Madras, but he finished his degree in IIT Kharagpur with Professor Sanjay Mujumdar in the physics department in IIT Kharagpur. And he did, a lot of atomic physics, theory of atomic physics at that time. Then he moved to Germany, first in Desi, Hamburg, where he worked with Robin Santra and some of the very exciting work he did there as a postdoc. And then he moved to the Max Born Institute in Berlin, after which he joined IIT Bombay in December 2015, and he has been a faculty over there ever since. Gopal's, of course, interests connect widely to things we are doing in TIFR, of course, with ultrafast lasers. And I thought it would be, he and I had discussed about this, and this would have been an ideal platform where we can, both at the Department of Nuclear and Atomic Physics, as well as in Department of Chemical Sciences, we have common interests. So we would like to invite. So Gopal, thank you for coming in, and he will talk about solids under intense laser pulses.
So I think so. Thank you very much, first of all, hosting me, and introduction, and I'm really honored that I'm in TFR and with this ongoing tradition of none other than great Baba. So today I'm going to talk about solid under intense laser pulse, and I hope at the end of the day, I may convince you that this route may be very useful to realize different kind of quantum technologies, especially at ambient conditions. So first, let me say what is intense laser means when I talk about. So let's see that the electrons in any system, it can be atom, it can be molecule, it can be solids, they are bounded by this Coulombic force, and this is the Coulombic potential. And if I want to draw this Coulombic potential, it looks like something like this, and this is, let's say, your steady state or static picture where both the electrons are in the ground state. Now, once we shine the light, and the light can be represented by simply electric field. So because it's electromagnetic radiation, and typically we are into the regime where the magnetic field of the light doesn't play any significant role. So only the electric field plays a role. So we can write down the expression of the electric field as amplitude times the oscillations. And if I want to see that how this electric field affect the let's say the electron, so it displaces the electrons from its original position, so it will create some kind of dipole, and the coupling of this electric field with the dipole is written in this simple intuitive form. So just to make the things quite simple, I have assumed everything in one dimension, but you can extend it to 3 dimension in reality. So what will happen when I shine this light, which is intense enough, and it's coupling this way? So what will happen? I can write down the total potential that is originating from your system, which is your atoms, molecules, or solids, matter. And due to this coupling, which is originating from light with the dipole, so this is what you find it. And now I can plot the total potential, and you see that this is your electric field. Okay, and this is your original potential, which is shown in a blue dotted line, 1 over x kind of things. But you see, this is nothing but like a straight line. So this really perturb your potential very significantly, and now your total potential is shown in a blue color. Okay, so the color is chosen in a same way, and that is what I mean by the intense laser matter interaction. So it's really modify your Coulomb potential in such a way that now this electron has a probability that it can tunnel it out. Here, this is a long range potential, so electron never tunnel it out. But once you perturb its potential or tilt its potential to a certain strength or extent, then electron has a probability to tunnel it out. And once this electron is tunneling out, then the things becomes very complicated. And like Professor Jyotisman is doing transient absorption spectroscopy within a pump probe scheme, it's not valid here. Okay, so what we call as in this particular scenario, when your Coulomb potential has modified drastically because this term start dominating over this term, then the standard perturbative treatment of light matter interaction breaks down. Whatever you have heard, like this pointer is in blue color, and the much cheaper version of this you can buy it in a red color. Okay, so what you are doing essentially, you are converting the red light into the blue light, red light into the green light by the frequency doubling. And this is called standard perturbative treatment of light matter interaction by converting 1 photon to 2 photon. And in this scenario, it does not work it out. So this is what is the impact of the intense laser. Okay, there's another scenario what Professor G. Ravindra Kumar is doing, that you shine a very intense laser and then you start ripping out the electrons and you create a plasma. So here we are not creating a plasma. So we are in between the two extreme regime. One is the perturbative regime and one is the plasma regime, and this is something in between comes out. And this becomes quite interesting, its own point of view. And that's why, because of the tunneling is one of the key steps, I will not go into detail maybe today. And because of this, last year, 23 Nobel Prize was awarded to the attosecond physics because the tunneling plays a very key role in generating the attosecond pulses and probing into electron dynamics of matter. Okay, so yeah, it's always this. So I have underlying assumption is that the wavelength is typically much larger than the size of the atom. So in a technical term, one could say that a long wave limit or dipole approximation. So because of the tunneling plays a key role, so we have these three scientists have received a Nobel Prize, which I will not go into detail. So when it comes to the matter, so let's say any solid or any matter has different kind of degrees of freedom electron associated with it. So for example, we have the charge of the electrons, and the charge of the electrons can be used to create different kind of transistor, and this transistor can be assembled to make different kind of these integrated chips, and then entire electronics is came out by utilizing the charge of the electrons. We can also utilize, for example, the spin of an electron, and when you utilize the spin degrees of freedom of an electron, you can make different kind of devices. These are the memory devices, and you can form a spintronic. So both of these themes are now well established, and these are impacting our day-to-day life. So you cannot run away either by electronics or spintronics. Now, in last 10, 12 years, there's additional degrees of freedom, and this is known as a valley. So what is the valley? Let me try to explain it. So let's say this is some kind of material, and you see that the atoms are arranged in a hexagonal pattern, and these are the two kind of atoms here. And now if you see this real space structure into how the energy of this matter is changing with respect to the wave vector, you can see that these are the energy versus wave vector diagram. And what you notice here, that this is your maximum of valence band, and these are your minimum of conduction band. And you see that at particular point here, or at this point of here, you have a minima in your conduction band. Equivalently, you have a maxima in your conduction band, valence band. Okay, so these are people typically called as a valley. So valleys are the minima or maxima in the energy landscape of any material, and in particular, by following the symmetry of this system, there are only two valleys which are associated at the two corners of this hexagonal material, and these are energy degenerate, so they have both are at the same energy. So the first question is that can we differentiate them? So to make this complicated picture much easier, so let's say when people talk about the valleytronics, it means that you want to do the same thing whatever you have done with the electronics, but not with the electronic charge, but with the valley degrees of freedom. So let me say that suppose you have the two valleys, and hypothetically, you do some kind of excitations in one valley without affecting to the other. Or you can do other way around. You can excite the other valley without affecting the previous one. So these two scenarios, I can visualize as 0 and 1. So these are now your two states. Either you are in valley 1 or you are in the valley 2, and the other valley is just a spectator. It's not affecting anything. Okay. So if you are into this situation, you are equivalently that your spin is up or spin is down. That's what you have, and the entire magnetism can be realized into this one. But the valley give you much more extra feature, that you can have also the superposition of the two. So you can excite here, let's say 70%, and here you can excite 30%. Then you have the linear superposition of the two valleys, and then you are into so-called quantum business. So this is the Bloch sphere representation of the valleytronics. Yeah.
Yes, just a quick question because I'm not from the field. How do you selectively excite the K
I will
and K
come
prime?
to this point. So far I'm in dream. So I will come how the people have realized it. So if you can also create different combinations, and then you can explore the entire Bloch sphere Bloch sphere of this K and K prime valley. Okay. So when people say, okay, my material is ready for the valleytronics, it means that it should fulfill these four minimum requirements, you are able to distinguish the valley, means you have the minima or maxima. You can achieve the polarization, means you can excite one over others or vice versa. Then you need to read it out, you need to detect it out, and then last is that you can have a control over this the way that you want. And if you are able to fulfill, then you are into valleytronics business. Okay, this is a technical term. Okay, so valley polarization or valley asymmetry can be obtained either by breaking inversion symmetry or time reversal symmetry. So for example, this system which I have started showing in the beginning, you can clearly see that if I'm sitting here, if you follow my pointer here, and if I draw a line like this, it has definitely inversion broken system. Okay, so this is not inversion symmetric system, and now I can choose different combinations of my blue and yellow. So these are the different combinations of M and X, and this is what is called in a technical term transition metal dichalcogenide, because these are two transition metal and these are the chalcogen atoms, and these are the entire family, and number of people in this institute are working this kind of material. So, and different material have a different properties. For example, WTE2 is semi-metal, MOTE2 is a relatively small band gap, but these four are very interesting material because their band gaps, the energy gap between the maxima of the valence band and minima of the conduction band, lies in the visible range, sometime 1.8 eV or something, and that's what people are doing a lot of interesting optics related to this one. Okay, so now there's a selection rule based on the Berry curvature, which is another technical term, and the magnetic moment. And what happened, we can discuss this in detail much later, that one valley is connected to the right-handed polarized light, whereas the another valley is related to the left-handed polarized light. Okay, and these are the pretty much selection rule, and people have derived it based on this selection rule. So these values in 2D semiconductor have potential for quantum information processing, especially at room temperature. Okay. Now there is a special problem that all the MOTE2 kind of things, MX2 kind of things, the way that you synthesize it, they are not free from different kind of defects. Then there's another problem that you cannot make a very homogeneous sample. So it means that if you create some kind of things and you want to propagate it, there's a possibility that these defects or some kind of impurity will affect whatever you have created. Okay, so you have problems with this one. And now the poster boy of the 2D material, and that is what we call as a monolayer graphene, because monolayer graphene was the first 2D material which was synthesized and which has been awarded Nobel Prize. So let's say, what about the valley polarization in the monolayer graphene? And so this is the graphene. So what is the difference with respect to the previous material? That all the atoms are homo atoms, and these are the carbon atoms arranged in a hexagonal pattern. And here you can see that this is a inversion symmetric system. Now, if I look at energy versus momentum relation, it looks something like this. It's well known for some of you. And you see that at some particular instances, your conduction band and valence band touches with each other, and your dispersion relation becomes linear here. Okay, so it means that you cannot do any excitations, unlike in the previous material which we have some band gap. So you cannot have any excitations at this point. Okay, so it means that zero band gap, and because of the band gap is zero, there is also comes with the price that the Berry curvature also zero. This system is not suited for valleytronics. So you cannot do any kind of valley related physics that you are exciting to one valley, not affecting to the other, because the band gap is zero. So where you are going to excite it? Okay, so that is the problem. Then another thing is that, especially in this vicinity, these are what we call as a high symmetry point or symmetry points. The total system can be represented by this linear relation k dot sigma, which I will come this point in a later part. By the way, among all the 2D materials, graphene is the one which has the maximum carrier mobility. So this is the best material for any electronic devices point of view. And this material is also quite good because it's cheaper and you can maintain the homogeneity for long way, because it's the mono atom things. So the conventional way for which the Nobel Prize has been given, the Scotch tape technology, which Andre Geim and Novoselo have used, it's much cheaper than buying the MOS2 or many other materials. Despite all the beautiful features, you cannot do the electronics. Okay, and that was the statement till every paper you read on this topic till 2021. The first line starts that among all 2D materials, graphene is not suited for electronics, and that things have changed after 2021. Okay, so the same energy spectrum I am now looking into the two-dimensional instead of one line cut. I have plotted into the two, and these are the same high symmetry point, and because these are the different triangles. So hypothesis is here. Suppose my atoms are situated at here or here, which is equivalently, let me go back to here. So this is my Fermi level, and electrons are sitting here and here. So it means that in the 2D picture, my electrons are sitting here and here. And let's say by some external force, I can put this electron here. It means that I can put the same electron here. Now this electron will see a different energy environment, than this electron. So if any particle situated at two places sees the different environment, it means that I have created a polarization. So I have created a valley polarization by putting the electron here. Equivalently, I'm putting the electron here. Okay. So that is the meaning of the valley polarization. So what I'm going to do, I'm going to sign the graphene by a combination of the two laser pulses, which combines one circularly polarized light with the left hand and another with the right hand with opposite sense of rotation. And the total electric field of this combination looks like threefold symmetric. So this is the legislative figure of the total electric field. Okay, and the sense of rotation doesn't change the this structure. So whether I choose the clockwise or anti-clockwise or vice versa, I am still having threefold symmetry. Two frequencies. Then how to combine the electric field? I can plot the total electric field. I can write the each. It will be oscillating differently. Yeah. So it will be oscillating. So this is a total electric field. No, what I'm saying is that you can't plot an amplitude there. This is the amplitude of one cycle of the total electric field. I can plot it. I can have any sum. I can have E1, E2, E3, E4, and I can add it. It can look any funny things. And this comes from the symmetry, because this is a 2, this is a 1, so this is a threefold. If it is 3, this is a 1, this will be fourfold. This is a very simple wave, this thing. We can discuss, maybe I can plot it. And now if you introduce a delay between the two, what will happen that this flower threefold start rotating in space. So this is the effect of the phase or the delay, and it start rotating it. So yeah.
So one cycle of omega is 2 cycles of 2 omega.
Yeah.
So the resultant is, what frequency is that complete picture?
This is the omega.
Omega.
Yeah, omega.
Okay, that's the amplitude at omega.
That amplitude at omega. So this is start rotating, and after 180 degree it comes back. So why it is interesting? Now let me put this electric field into the valley perspective, and you see that at 0 degree, this electric field fits with one valley perfectly, but it doesn't fit to another valley. Now if I change my phase from 0 to 90, it fits to another valley perfectly, but not to the one valley. And that's what I needed. I needed to create a polarization. So you see, this favors to one valley, but it doesn't favor to another valley. In this case, it favors to this valley, but it doesn't favor to a previous valley. And that is the meaning of the polarization. You favor to one, you doesn't favor to another one. Okay. So let me show the results. So these are the results. So what I'm plotting here, I'm plotting the population in the conduction band after my laser pulse is over. So the difference of the population in K and K prime valley with the normalization. And here are the different polarization which I have shown you, and you can see that I'm able to tune the polarization from minus 0.4 to 4. So 40% valley polarization from one value to another value. So this is what I'm able to do it, and I can oscillate it properly, because after 180 it starts repeating, and you see that at 45 degree this structure doesn't fit to any of the valley. So at 45 degree I have a 0 valley polarization, because it doesn't favor to any of the valley, so it cancel it out.
Can I ask a question?
Yeah.
So in time, when t equal to 0, you still have both the values getting excited, or one of them is getting it, and after say time t equal to tau, you excite the other value when the polarization has
Very good question. So at time t is equal to 0, none of the values are excited.
excited. Okay.
As the time progresses, I am exciting one
Select-
value with, let's say, x amount, and another I am exciting with, let's say, y amount.
Okay.
And I can reverse this by changing the phase. So
Okay.
either I can make x larger or y larger.
Okay.
And when I say x is much, much larger than y, or y is much, much larger than x.
But
So
this is cycling again
this
and
is the
again, back and
cycle.
forth.
So that's why I'm plotting after the pulse is over. So now I have switch off my laser.
Okay.
And then I'm looking how my population is doing. Of course, if I look longer, like picosecond or nanosecond, then everything will die down. I will come to this point in a later moment. I'm coming now. Yeah.
You're talking about how much of the 2 omega do you change the mixture even and
I will come to this, both the points. So intensity is plotted here. So you see that this green curve is the light at phi is equal to 0. And if you see that intensity at 0.51 into 10 to power 11, you have no Weyl polarization. And then after a threshold, the Weyl polarization started increasing linearly. The region is simple. Your electron is sitting here. And if you give a kick, a small push, it will be still within the homogeneous or isotropic region. So you need to take this electron to the anisotropic region so that the Weyl polarization can be developed. And the linear region can be understood very simply because whenever you kick anything, the force is nothing but the electric field times charge. So if you convert this thing into momentum, momentum is nothing but momentum follows the linearly with the vector potential. K becomes K plus AT, or P becomes P plus AT. That's what we learn in simple quantum mechanics or classical. And that is the linear behavior. Okay.
what's the wavelength that you use in this?
So here I have used 3.6 micron. But now one could ask how the results are changing. So these are the scan that we have done it. So this is from 3 micron to the 6 micron. And these are the different intensity of my fundamental pulse. It's omega. And you can see that you can reach up to 60% Weyl polarization.
So why this wavelength region? I mean, what's special about 3 to 6?
No, I can choose 1 or 800. Okay. So there's another reason people started developing mid-IR laser, because you damage the sample. So you don't want to damage the sample, but want to keep the intensity same so that you can see the nonlinear effect by increasing the wavelength. So that's why we have a long wavelength thing. Okay. So you can see that by different parameter range, you can, right? And now you can transfer the entire plot into the scattered one. And here you can see the same thing, whatever I have alluded just now, that you see up to a certain value of the vector potential, you don't see anything, and then you see a linear increase, which is nothing but a K plus AT.
Is this experiment? Or
No, this is the data. This is the data, scattered data. So this is the 2D is converted into 1D.
Is this coming from experiment, or
these are the theory,
or just
only theory?
only theory?
Okay. So now, once this came out, because
Sorry, if you go back to the tunneling picture, what's happening when you impose this omega to omega? In graphene, what exactly is happening?
Okay, so in solid point of view, what happened? You have a periodic potential. Let's say very penny model or whatever. And in a real space picture, what happened that your potential get bent like this?
Oh, that I agree.
Yeah.
But in graphene, what's happening? I mean,
It
you said
becomes
that
much
this
more complex.
dispersionless and all that.
It becomes a much more complex structure which cannot be plotted. So that's why, I'm sorry, little bit deviating. So that's why people thought that, okay, we will change the polarization from linear to circular, and we can generate the harmonics. And what they have seen that harmonics drop out 0. The reason is that the tunnel electron never comes back because it's like a drag and it drops out. So people never get circularly polarized higher order harmonics in a strong field using a circular polarization in atoms. Okay, so once this, yeah.
You said that it's like a conic model, it tilts, and the electrons
Run out means what? Yeah, I put a light and then I get a current out of it.
No. So what happened? So you have a periodic potential. Now, because I have signed the strong electric field,
Yeah.
so it will modify the potential. So potential get
Right.
modified, and now the electrons are tunneling out.
Yeah, tunneling out, but then what to do what?
No. Now this is your electric field.
Yeah.
So after first half cycle, the lower cycle will change its direction.
Yeah.
So then I will change this direction.
Okay.
So it means that whatever has been tunneled out, it will recombine back.
Okay.
So then you have a what is called block oscillation.
Yeah.
So that's what you can have a block oscillation.
Oh, sorry. I thought that you said that there was something complex which you couldn't plot.
No, you cannot visualize how the tunneling will happen in a three-dimensional way. I cannot plot it. In 1D, it's very simple to show that, okay, your potential, bend it out. But in two-dimensional, you first plot the potential, and then you need to show the bend.
You said can't be excited because of.
Yeah, okay. So, I'm sorry, very good question. I'm sorry. So, what we are doing here, so we cannot excite it, as you agree. So these excitations is what we call, as in a technical term, is interband transition, because it's going from one band to another band. Okay, and what we are utilizing first time is intraband transition. So it is going within one band, because when the two bands are touching with each other, it can be seen as a one band, and then I'm climbing over one band slowly. So these are the intra-band driven processes, and it has its own benefit, which I will emphasize maybe in few slides later. So it's not the direct transition, but it's intra-band. So once this came out in 2021, it becomes quite hot topic worldwide, and the Forbes magazine started saying that it can be top 10 omnibuses for the exponential impact. Even it can be a top trend in the quantum technology. Now you may ask, okay, so much hype, what else? So I will not discuss the detail of the experiment. So this is the first experiment done at ICFO Barcelona. What they have done here, bulk MOS2. Bulk MOS2 is inversion symmetric, and they use the tripole symmetric light what we have used, and they have seen the valley polarization. Okay, exactly the same thing they have done it. So it's not going excitations, but the mechanism that we have suggested.
That valley polarization, the data.
These are the theory. But this entire paper has so many pictures. I have not put.
What are they measuring?
They are measuring the. Okay, so you can measure the harmonics.
They are measuring.
Okay. Then simultaneously you can see the dates. Simultaneously, there is another paper from the Slack group who have done the same experiment, but not in bulk MOS2, but in monolayer of HBN. Here also they have used the omega 2 omega, and they have given some fancy name, which I don't want to go into detail, but these are the main message that, okay, the tripole either touch the same kind of atom or another kind of atom, and in this way, yeah, this is from your previous member of here, yeah. And then there's another paper which came in archive from the Langen group, Germany, from the Peter Hamelhoff, and they also use the same combinations, and this is done in graphene, and they can see the valley polarization. So these are the three paper came out this year, two in published one, and this is under review, and this paper uses much more than what we have predicted, but this is the key idea. So this has been realized. So bulk MOS2, monolayer HBN, monolayer graphene. So this becomes trend. Okay. Now the question is, when you talk about the quantum technology, it's not only you create a polarization and that's it, because that's how not any device will work. Device will work, you have to create, the first step is transistor. Okay, so what is the transistor? Suppose I am in this state and I want to go to this state on the fly. So one option is that, okay, I can wait, my population will come down, I change the configuration of my laser, and then I can excite it. This is a very simple way. But I want to go from here to here in the non-equilibrium state, and how I can go it. So the idea is that we are going to use the linearly polarized light, and this is now cos omega t plus there is a phase, and this phase is called envelope phase, and the region of this phase is that when the cycle or this cosine omega t is matching with the envelope of this short pulses or not. So if both are matching, the CP is 0, and if they are offset by 90, they can be offset by 180 degree. And now we are going to utilize this CP of short pulses to create the transistor. Of course, electric field is related to the vector potential, and here is the vector potential. And you see that once the electric potential is going, you are creating the population in the conduction band, you are exciting in by intraband way, and now you are coming back. So as the direction of your electric field is changing, the direction of your electronic motion is changing. And because it's coming back and forth, so that's why you are seeing the interference pattern. And the simple reason is that now if I draw a line at 0 by visible way, I can see that I have more red than the blue. So I have some kind of polarization. The reason in a very simple way can be attributed that if I draw a line here, I have a more one direction towards other direction. So my waveform is asymmetric, so that my population is also symmetric. So I'm really imprinting the waveform asymmetry to the excitation asymmetry. So I will come to this point, okay? So now if I have a 90 degree, so if I draw a line here, you can see that I have both red and blue equal amount. So both are occupied. And if I change the 90 to 180, then I have a more blue to the red. So now I'm ready. So I will send the 3 pulse with different phase value. First, I will create more population over one valley than the other. In a second pulse with different CP, I will equilibrate it. And in the third one, I can go to other side. So I have created from one side to another side, and that is what switch by combination of the 3. In a technical term, if you want to call it, this is a coherent control. Okay. So I'm coherently controlling it. So here is the results. Let me come back to the result.
Each pulse is a combination of that omega and
No, here is a linearly polarized pulse. Just one frequency, linear polarization, no circular polarization. So this is a graphene, and you can see that in the first step, I have a more red. In the second step, I have equilibrated. In the third one, I have created more blue. So I have gone from one valley to another valley. Now what I have done, I have just changed my system from graphene to MOS2, and the entire setup remains same. I have not changed anything, and the physics is same. So this is result for the MOS2. This is the result for the graphene. So this I have done it. Now the question is how long it can be lived. So first of all, we have tested for different wavelength, different delay between the 2 pulses, and they are surviving up to 50 femtosecond or so. Okay. So now I will not go into this part because this is still under review. We have also devised with a group in IIT Kanpur, where we have collaborated, where we are signing omega to omega, and here you can make some kind of tunnel devices with the graphene nanoribbons, and here you can see a valley valve or valley filtering. Okay. Now let me pause a moment and give a thought, because that is the important thing about this work. So currently, quantum technologies are based on mostly from 2 approaches. One is the trapped ions, and another one is the superconducting qubits, and these are the transmons qubit. And both of these architectures are quite bulky. You can see the structures, and both of the architectures are kept in a cold temperature. The reason to keep this in a cold temperature is that you don't want to destroy something is called coherence or qubit. So you have prepared something, and you don't want that the neighboring things will come and scatter it, so that whatever I have prepared, it will be destroyed. So you want to avoid the decoherences, and that's why you have kept in a cold. Huh? No, trapped ions are already in a cold temperature. They are not in a room temperature. They are at least in a micro. No, it doesn't require cooling, but the trap, when you say that I have a trapped ions, it means that I have already cooled down to at least micro. It does not require any cooling component. No, it doesn't require extra. I agree. Yeah. But these are already in a very low temperature, not at a room temperature. Let me put in a very simple way. Okay. So if you think about that if you want to have some quantum device based on either of these two approaches working in this room, not going to be possible. Okay. First of all, it's bulky and you need to have a cold environment or not ambient temperature. Okay. So now there are one parallel hypothesis which we are putting forward, and we have put it that, see, the way that we are creating the valley polarization and we are creating also the transistor, these are really short pulses which are lasting 20 femtosecond or 10 femtosecond. We can also do the same kind of experiment with the attosecond pulses now. Okay. So, no, femtosecond now you can have really compact one. The fiber one which I have seen
The
is
strapped ion system is much more compact.
okay. I don't work on the trapped ion, so I cannot say it, but at least I can only talk about the environment point of view. So maybe in future people can come up with much smarter idea. So the idea is that I have created the coherence between the electrons, and this coherence will be lost whenever I have some other agent, means that either the phonons are coming into pictures or some kind of scattering is happening. And these are going to happen in a much longer time scale, which are hundreds of femtoseconds. Okay. Let's say that is the typical time scale of any phononic or any scattering, right? So the idea is that you can do the measurement 100 and 1000 times before any decoherence effect come into picture, but at the room temperature with the graphene or MOS2 kind of devices. So that is the idea. Okay. Now, if you ask, 1 minute, let me make a disclaimer. If you think that it will come tomorrow, I don't think so. Maybe down the line of 10 years, maybe this idea will be die down. I don't know. But this is the at least only viable option one could think of if you want to bring the quantum technology at room temperature or ambient condition. Yes.
Nice idea. The question would be, at what time scales these individual pulses would be? They have to be shorter than the lifetime of the coherence. So they have to read out things. Also, what is the rate at which errors will be created? And what is the efficiency of the entire process?
Okay, so the error and efficiency I cannot talk about, but the pulses are going to be much, much shorter than any of the effect or anything happen. So because you are just manipulating the electrons the way you want to do it. So you change the pulse form, you change the pulse duration, and the effect is going to be longer. The other thing is that
And the damage threshold?
these are below the damage threshold. So you see that now people have performed the experiments. So these are the two experiments which are the evidence. So when we published this paper first in Optica, first we put in some other journal, but people thought, no, this is not possible. But now the two paper back to back in Nature showed that this experiment is feasible. No doubt about it. Now, the way the coherence is created in our case, in the first case, or even in the second case, is via intraband motion. So the thing is that if the electron is going from one state to another state by interband, it also come back quickly, lifetime. But if it takes more time to the climb, it also come back slowly. So the coherence, which you don't find in literature in general, the coherence created by the intraband dynamics is much, much longer than the coherence created by the interband dynamics. So because intraband is still not very well explored because the field were not strong enough to drive the electron the way you wanted, but at least this is the picture. Now, let me come back to another aspect in quickly. So far we can use the tailored laser pulses, we can make a switches. Now, after this graphene, people thought that we can have the equivalent material in 3 dimensions. That's what the thought, that we can have some material where we have the dispersion linear. Okay, so the first thing they thought, okay, let's do it. And this is what we call as a Dirac semi-metal. And these are the few realization of Dirac semi-metal where your linear dispersion is here. Okay, and this along this point, still you can describe everything by linearity. Now, these are the real RFS data which has the linear dispersion. Now you take the Dirac semi-metal and either you break the time reversal symmetry or you break the inversion symmetry, and what you will get what is called the wild semi-metal. Okay, and these are the few wild semi-metals material, and these are these are the few Dirac, and these are the few wild semi-metals, and these are the non-magnetic and these are the magnetic one. But why these materials are so exciting? Because the collective excitations of these materials, people thought that it can be described by the Weil equation or Weil fermions. Weil fermions, when Dirac wrote its equation, Dirac equation, Hermann Weil wrote within a few years later an equation for a massless fermions. But these massless fermions must be chiral in nature. Okay. And that's why people thought that, okay, maybe the neutrino are the right candidate for the Weil fermions, but people later on figure it out that, okay, these are not the right. So in high energy physics, people never found any analogous Weil fermion signature, but in condensed matter physics, people found that, okay, these materials are the Weil fermions, or Weil semi-metal is a well-known material. So these are the touching points, but what is the beauty that these touching points serve as a linear dispersion in momentum space, and they work as a monopole because they will always come in a pair. So these are the Berry curvature in the valley points, and these are the topological. So whether you put any kind of defect, you put any kind of external perturbation, you don't destroy this topological nature. Okay, so that's why wild semi-metals are topological in nature. So what is interesting so far? So these are the linear dispersion, and there's a similar kind of selection rule. So you can excite one part of the Weil cone by the one helicity, another kind of by another helicity. Now, in 2017, 2018, 2017, there's a group from MIT, and they wrote this famous paper where they said that, okay, we can read out the chirality of the Weil fermions by pump probe approach. So reading the chirality of the Weil fermions was the first thing or important things, because it shows that, okay, these are the truly chiral in nature and these are the Weil like particles. Okay, immediately this paper, and the reason for this one, okay, if you have the Weil fermions, first of all, you need to, these are the selection rules, so you need to break the inversion symmetry, and you need to create some kind of imbalance, which is, let's say in this case, Pauli blockage, and then you can measure the photocurrent, and photocurrent has its own helicity. So after this paper, there have been series of papers which said that, no, the signature that the MIT group has got it is not correct, because you are exciting too far away from the band touching point. So you need to excite using the terahertz, because terahertz has a small energy, so it will excite very close to the touching point. It will not excite in the micro region. And then people said that, okay, we can have a type 2, this is a technical detail, you can ignore it. So what people have so far thought that, okay, while nodes opposite helicity, they have to be at different energy, inversion symmetry must be broken, Pauli blockage play a crucial role, and you need a terahertz. But so far, there is no conclusive evidence that Weil fermions have a definite chirality by any experimental evidence. Okay, so we thought, okay, let's try to prove it. So we took magnetic material, it's FCC material, and these are the two Weil cones, and these are the parameter lattice parameter. This is the band dispersion, and if we look in the three-dimensional along the z axis, it looks pretty isotropic. And this is inversion symmetric because this is a magnetic, so time reversal symmetry is broken. Because for the Weil semi-metal, you need to break one symmetry, either inversion or time reversal or both. We got very puzzling results. So what we did to understand the entire result is we expanded this Hamiltonian in power series, because we can write cosine sine as a k square and all these things. And we kept only leading order term. So when we kept only leading order term, we got the entire equation like k dot sigma, whatever was the linear one. Okay, so we went one step ahead, and what we did, we excited one Weil cone with the LCP RCP, and both are slightly distinguished because, as I said, that there's a preferred selection rule. We excited another chiral Weil points, and they are doing this. Now, if I excite one with the left and another with the right, and put the top of each other, they should have like the same, like chiral molecules. You take the chiral molecule, excite one with the left-handed molecules with the left-handed right-handed molecule with the right-handed right, and if you put both supposed to be the top of each other. So that's what we did. And if you see that they are top of each other, so it means that they are truly chiral in nature. when the dispersion relation is described as a k dot sigma. And because both are symmetric, so you cannot have any photocurrent, because whatever you are exciting this point, you are exciting this point, and they are opposite in nature, they will cancel it out and there will be no current. Now we can expand to the higher order term. We can go to the k square, and when we went to the k square, the things becomes very surprising. Let me run it out quickly. So when we excite the k square, both are not matching with each other. Okay. And here we are doing systematic study, because in real material, we don't have this kind of freedom that we can go to the k square, k cube every other term. So here you can see that when I put the reverse the things, solid from blue and dotted from red here, they are not matching top of each other. Okay. The same is here. Now, if I go to the realistic material and I'm again plotting the same asymmetry, you see that these are the position of the wild points and these are the asymmetry, even if I have almost like a terahertz, 10.6 micron. So I went from 1.6 to 10.6, and whatever wavelength I'm choosing, I'm still getting asymmetry in the population. Almost. Yeah, I can keep going, but it doesn't change the physics. Also, here are the different wavelengths, and you see that the asymmetry is of the order of 1, and if I plot the deviation of my dispersion relation away from the linearity, the order of magnitude is 10 to power 3. So it's nothing related to how much your dispersion is deviating from linear to non-linear behavior. It's a truly inbuilt problem. Okay, we can tailor the intensity from 5 into 9 to 10 to power 11, different intensity, still we have the same thing. Okay, so what we can conclude, and why people are not able to see the true nature of the wild fermions, because the wild fermions are not truly massless. Because how you define the mass of a particle in a solid? The curvature of the band. And if your curvature is not going to be linear at any cost, then they are not massless. Okay, so that is our conclusion. And because now you have asymmetric population in 2 different wild points, 4 different wild points, then you can also now create a photocurrent, and those do nonlinear optics. They know that inversion symmetric system cannot generate photocurrent or rectification. Second order nonlinear effect is, but by doing a strong field or intense field, we can create. So this is one where we talked about the wild semi-metal, and this is another paper where the photocurrent can be generated using the linear pulse. So the summary of the last part is that wild fermions are not truly massless, and that is the title of our paper, that are the wild fermions are truly massless. Okay, so even longest wavelength, weakest intensity, whatever we have apply, we cannot get away from the touching point. We have to excite away from something, and non-linearity will come into picture. Okay, and the origin is also attributed in a technical term to the Berry curvature. Okay, so this work was done my student Amar, most of the wild things, and in collaboration with Misha Ivano. And we also did some work on the Majorana fermions. I'm not going into detail. So with that, thank you very much for your kind attention.
Okay. Thank you, Gopal, for a very exciting talk. Questions for Gopal?
Maybe I have went a little fast in the last part, because I thought maybe I don't want to keep you.
You know, the omega to omega paradigm,
Yeah.
it's become so well established now for coherent control from the 80s
Yeah.
onwards for gases,
Yeah.
terahertz generation in gases and so on.
Yeah.
But the electric field is actually very different from an oscillatory electric field, right?
Yeah.
Because you have 2 frequencies, a harmonic and a fundamental mixing up. And if you plot the result, it is actually highly modulated.
Yeah, so depends on what is the polarization you are using.
So you're using LCP and RCP. For,
yeah.
So orthogonal.
Yeah.
So that's another thing. I don't
know. Not orthogonal. They are on the same plane. So LCP, RCP, both are on the same plane.
Nevertheless, so it doesn't give you a purely oscillatory pattern. In fact, the reason terahertz is generated, because it generates in gases, for example.
Yeah.
Because it gives a directional motion to the electrons.
Yeah.
Which is not purely oscillatory.
No, it will give you the oscillatory motion, and this is the true picture that they have plotted in the experimental paper. It's the threefold symmetric. Yeah, so this is threefold. Now, because when
This represents the electric field.
this represents the electric field, this represents the electric field. This
I
is the
see.
trigonal
This is
fold.
at,
So you see, you have a pulse, you have, let's say, the 10 cycle.
correct?
So at the top, you will have a maximum big flower, but then slowly, slowly it will keep rotating and going.
No, what of the electric field are you indicating here?
The total electric field, I can write down,
So,
please allow me.
yeah.
So I can write down so now this electric field for a single cycle of in units of omega, it will have a threefold symmetry.
Amplitude of the
I have assumed it that amplitude of the 2 is twice the fundamental. Yeah, but I can have any value. That will change that will distort it. But it is quite easy to do this kind of things or half because generally what you have generally that E2 omega is typically half of the E omega.
So why take harmonics? Why? I mean, let's just take two different frequencies.
Why you take threefold? Why you take
Why do you
omega
take
to omega?
harmonics, yeah? Why do you take harmonics?
Because no, first of all, you cannot take the non-integer value, right? You can take
No,
omega
just
to
take
omega.
omega 1 and omega 2, for example.
But you need a threefold because the threefold fits with the threefold structure of this thing.
Okay, but in general, you don't need to, right? I mean,
No, then you cannot have.
Depends on what structure.
What structure you
what
have?
is exactly what is the
Underlying
shape
symmetry.
of the light pulse that you're creating, the electric field that you want to
Yeah,
generate, and matching it with this.
Matching with this one.
So that's the reason.
That is the reason. So we also tested in, I have not put the result, but we also tested omega 4 omega and it had the fourfold structure and it gives you zero value polarization because it doesn't fit to any of the values.
You're estimating value polarization.
What is the difference in the strength of that blue versus red curve that you were showing? What is the percentage of polarization that you're getting?
So let's say we are getting something like 30 versus 5 or something like that. This can be improved by increasing the intensity, but at some point in time, if you keep increasing the intensity, you will start mixing the population from one region to another region, then everything becomes blurred. So the boundary becomes ill-defined. So you cannot keep increase the intensity a lot. Also, if you keep increasing the intensity, you also damage the sample. So, or you can keep the in an ultra cold temperature, but that's people don't want.
But then isn't your performance of your transistor depends on how well you are polarizing this?
No, the transistor is based on the linearly polarized. So linearly polarized will have less intensity.
A quick one, perhaps.
Yeah.
Is there an independent way of ascertaining the resultant polarization of this addition? Can one set up an experiment just to confirm that you have gotten the threefold polarization by adding 2?
This is a very simple thing. You can add it, you will.
Do you see it in the experiment? Is there an experimental setup which shows that, look, I have measured it?
Okay, so people generally measure the electric field or the vector potential of your light by streaking or by equivalent the frog crab method. But generally these methods are only valid, are mostly applicable to the linearly polarized pulse. People have never thought to put it into the 2 dimension, but what people have done it, let me tell you. People have done fragmentation study because these pulses are also very useful for the chiral, because left-handed light is chiral in nature. So when you take the combination of the two, the total electric field is also chiral in nature. And what people have proven that this will improve the chirality or the circular dichroism, it enhances the circular dichroism. So what they have done it, they take the molecule and ionize this thing. And because your electric field is threefold, the atoms, whatever you see in the mass spectrometer, it shows you the threefold structure. So that's what people have done it.
The
Momentum imaging, yes, thank you. Yeah, momentum imaging. So this way they have verified it. But one can plot it. It's not simple one. You put one value of omega and that comes out as a threefold. So it's a simple 1 to 1. It will be twofold, 1 to 2, threefold, 1 to 3, fourfold, and so on and so forth. That's what they have also done.
Electrons carry the momentum.
Yeah. So that's what they have done when they have also done the chirality. So the photoelectron circular dichroism, PECD, they have done it. Yeah. Because this is a completely separate issue of the atom and molecule. So I have not brought this thing.
Okay, I have a related question with regards to detection.
Yeah.
Nugedik's group, which you later showed, had done some photocurrent measurement. What did Jens Bigger do in this? How did they see, you said about harmonics, some detection of harmonics.
No.
How are they detecting the signal that you have, that there is a polypolarization?
Okay, very good question. So let's say I have inversion symmetric system. So I will not get any even order harmonics. Agree? Right? Now I'm sending omega to omega. So there's a selection rule. And what you will get omega, 3 omega, 5 omega, 7 omega. You will get up 2 omega as a 2 omega. And then you keep counting as a 5 omega and so on. Okay?
So not getting a signal means there has to be a contrast.
No. So you are not going to get the harmonics at the 3 omega and 6 omega. Logically, right? So now you have created the valley polarization, and what they have sent another linearly polarized pulse with frequency 3 omega, and because if the symmetry is broken, they will get the signal at 6 omega or they don't get a signal at 6 omega. And in this first paper from the ICFO that was proposed in our Optica paper, you get the signal at 6 omega. And now you can also read out the phase of the 6 omega. If the phase is, let's say, with respect to whatever, positive or negative, then you can say that this is my valley 1 or valley 2. Depends how you use the convention. Okay, so somewhere we have, I think, phase reading, but they have followed the same, this thing. Both the paper actually followed the same idea of the using the another, okay, let me. Yeah, so this is another thing that people can do it, that if you see that how the harmonics, let's say the fourth, fifth are coming, you can see that which is dominated by which one. This way also they can read it. So this is also we have done it. So because a higher order harmonics require another 5-10 minutes, so I have skipped the reading part. But that was originally done in our paper, which they have followed it.
Any more questions for Gopal? If there are none, yes, sorry.
One line I understand without final interest, then that wide point I cannot access simply because it's a proper overlap point.
Yeah.
I'm always going to make any transition, it's always going to be off that point.
No
matter which wavelength you go in,
yeah,
you'll always have a mass.
You always have a non-linearity in your dispersion, so you always have a some mass. So then the notion of the chirality, which Hermann Weyl has predicted that these are the Weyl fermions with chiral nature, need to be revisited in the context of the condensed matter. So most of the papers you read it, they say that these are the Weyl fermions, collective excitations. that has to be taken into different account. Yes, yes.
Everything is happening in one side.
No, these are multiple cycle. These are the 100 femtosecond pulse with 9-10 cycle in valley polarization. So I'm looking always everything after the pulse.
But there has to be some overlap.
No, so this is happening in 10 cycle. This is only I have written the electric field. I can now add the envelope here. So that's why, because of the envelope, yeah, because of the envelope, you see change in the amplitude, because your electric field is changing as a function of envelope. So the total field is also changing as a function of envelope.
Carrier frequency is still visible. Your gap is so small.
Which gap? So these are the electric.
Zero gap. So the excitation would occur very far from the light point.
The key.
No. So it start wherever the electrons are there, and it start putting the force towards the direction of the electric field.
What is the significance of having a zero gap?
There is no significance. No. But we wanted to show that you can have valley polarization in a zero band gap material, which people have said that it's not possible. Yeah, this
And
is the
also
only
that the intra-band relaxation
because
is
it's
slow.
the intraband is even slow. So from
That's
the device point of view also, getting a clean sample of the graphene is much easier than getting a clean sample of MOS2 from many point of view.
That's
And one thing which I have not discussed because of this audience point of view, whenever you talk about the MOS2, you need to invoke another notion is called exciton. In graphene, you don't have excitons. So you are win-win situation in every point. I have avoided a lot of technicalities because not maybe people think what is the exciton you're talking about.
okay.
Yeah.
Thank you, Gopal. That was very nice. Thank you very much. And I request all of us to walk down with Gopal for some snacks to the West Canteen. Thank you. Very interesting.